Okay, now what we're going to do is we're going to look at strategies for evaluating limits. The first thing that we want to talk about is the most obvious and the first resort that you will do when you're asked to evaluate a limit, and that's called just simply direct substitution. You always want to do this first. Now, unfortunately, about 80% of your questions will not allow you to do this, but the easy questions, the 20% maybe, will be able to be solved by using direct substitution. Pretty straightforward. All we want to do is to substitute your x value into your function. So here's a couple of examples. Let's look at the one I've put my arrow towards. I'm looking to find the limit as x approaches 3 of the function x squared plus 5x. Now, the direct substitution, like I mentioned before, is not used too often because, like I said, it's more of the basic questions. You'll know basically when you can use direct substitution. You will always be able to use it for the questions that do not involve the denominator. Any questions that are going to not result in a question being undefined or having a 0 in the denominator, direct substitution is probably the way to go. Be careful of radicals, of course. If you get negatives underneath the radical sign, direct substitution obviously will not be your desired choice. So anyways, let's look at the one on the left here. Just focus on that. We're just going to sub 3 in for x. Pretty straightforward. And the limit as x approaches 3 is going to be 24. The one over on the right, it does have a denominator, okay, but fortunately for us, we're approaching positive 2. So when we use direct substitution, we're not going to get a 0 in the denominator, as you can see, and we just simplify as you would in any other math class you've taken up to now, and I get an answer of 2. So that would be the one that has that x approaches 2 for that function. Pretty straightforward. Like I said, not used too often. Sonny analysis is another method that you might want to choose if you have if direct substitution fails you. So basically what it's saying, we've got a limit as x approaches b. If by direct substitution, when x equals b results in an expression of the form something over 0, you know that there's going to be a vertical asymptote when x equals b. So we want to use a sign analysis for that. Okay. So we've got 3 examples here. The first example is basically the same as the second example, which is leading up to the third example based on left-hand limits and right-hand limits. And of course, we'll just evaluate the actual limit, ignoring the fact that it's left or right. So in the first question, I want to make sure that we're all okay with this, so Lana might want to watch this. We've got the limit as x approaches 3 from the right. That's not saying as x approaches positive 3. Do not forget that. Okay? This is x approaching 3. This is x approaching 3 as well. It's not negative 3. Okay? But the negative sign refers to the direction in which you're going to travel. So we're still approaching 3. Now, if you were to use direct substitution, if I plug in 3, I'm going to get, in my numerator, 6 over 0. So that's a situation where you've got the c over 0. C in this case happens to be 6. Doesn't matter what c is. What matters is you have resulted in a 0 in the denominator. So we can't use direct substitution. So let's use sign analysis. What we have written in type there is just basically what I mentioned on the previous slide. You're free to read that on your own time. But here's my sign analysis. Okay, so I set up my 2 zeros. Zeros meaning when I set this equal to 0, and I get negative 3, and that goes there. When I set x minus 3 equal to 0, I get that 3 there. And then of course we just did the sign analysis. So resulting in a positive region there, a negative region, and a positive region there. And notice that we have a 0 where that blinking cursor is, because when you plug in -3, you do not get 0 in the denominator. You'll get 0 in the numerator, where you get -6, so it would be 0 over -6. So the value of -3 is 0. Okay? The value in x is 3 will be the resulting infinity. Okay? So that's kind of important. I want you to get used to starting to write what the value is underneath your zeros. Remember, these are called zeros, but in calculus, well, we call them zeros in C30, B30A. I'm going to call them critical points from now on, because they're not always zeros, as you can see, because this one wouldn't really be classified as a zero, would it? Because it doesn't result in a zero. It results in a vertical asymptote. So for me to define them as a zero is kind of incorrect. So I'm going to call them critical points, and you'll hear that word a lot more in the future. So anyway, I want to make sure that I remember back to my question what I'm actually looking for. So the first one, I want to know the limit as x approaches +3 from the right. Let's look at my sign analysis. So I'm approaching this value from the right. Now from the right means you go from right to left. So I'm going to travel in this direction. Here's where your sign analysis helps you to determine what type of limit you're approaching. Well, if you can see on the right-hand side, I've got plus, 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 so on. So as I approach infinity, I'm going to be approaching positive infinity. And you can see, I can't quite see yet, but when x approaches 3 from the right, we're going to be approaching positive infinity. It's very nice how the sign analysis tells me that. Now as I approach 3 from the left, which is your second question, or question B, I'm approaching +3 from left to right. You can see my function is approaching negative infinity. Very clear for us. Okay? So if my right-hand limit approaches positive infinity, my left-hand limit approaches negative infinity. If I go back to the third question, what would we say for C is going to be our value? Does not exist. Good. That does not exist because our left-hand limit doesn't equal our right-hand limit. I think that is something that is clear from yesterday's assignment. So, when I move screen shade here, notice I did have to make a little, there was a typo in the notes. So in question B, the fellow who made these notes forgot to put the negative sign with the infinity. So you can see, some of you might have it in there, some of you might not. I might have caught it before some of you printed, but if you haven't printed it, it will be on there now. But you should insert that negative sign with the infinity. And question C just goes on to explain that if your left-hand limit does not equal your right-hand limit, then our limits will not exist at that actual point. Alright, so I'm going to give you guys some time to work on this question. It's basically identical to the last question. There are 3 questions, but they're all related in the sense that we're approaching +2 from different sides. The first one's from the right, second's from the left, and then we're asked to evaluate the limit at that point. So I'll give you guys a few minutes to work on this. I'll come back and I'll check in with you in about 5-7 minutes. Alright, another option that you might run into is evaluating limits when you have to factor first. So, with direct substitution, we run into a different type of problem. We run it now into a 0 over 0. Okay. When you see this situation, what should come to mind is possibly looking to factor to get rid of that particular situation. Now, if you were to just look at this question, if I plug in 2 by direct substitution, I am going to get 0 on my numerator. Just to prove that, x squared, so I've got 2 squared minus 0 in my numerator, and quickly on the bottom, you'll get 0 as well. So, I get a situation where, wow, right? Obviously the limit is not going to be 0 over 0. The limit can never be 0 over 0. So, what we possibly want to look for is the factor. So, without me having to show you this slide, and to show you how to do it, I think we're all capable enough to factor that numerator and see if something cancels. If something does cancel, please do. Once you've canceled, maybe now you can do direct substitution and see if you have a limit will result. So, what is the top factor here?
X minus 2 and X minus 3.
There's some more there that I just mentioned. Bailey said it was X minus 2 and X minus 3, so that's still over X minus 2. I can cancel my X minus 2's. And I get a value of -1. Now, you guys still there? What I want to talk about is consistency and I guess mathematical professionalism, if that's the word I want to use. In your questions, when you do your limit questions, I want to make sure, and this is how you will be asked to do it next year and the year after and the year after that, depending on how far you take your mathematics career. Direct substitution probably can be done on a piece of scrap paper or in your head. You see that we result in 0 over 0. Here's how you have to proceed. Okay. I wrote down my question, the limit, and I wrote down everything. I wrote down LIM as x approaches to, and then the particular function I was dealing with. The next step, I wrote directly underneath. I'm not writing to the side. I'm not writing over here. Right? You have to follow in a vertical column. Right? And once again, I've got limit. All I've done is I've just factored my numerator. The next step, I've got limit of x minus 3 all over 1. Right? If you didn't write the over 1, I wouldn't be too disappointed. What I will be disappointed in if there's no limit. Now the next step, the author did not get lazy and forget to write limit. You stop writing limit and you start substituting a value, so you can stop writing when as x approaches something, when you begin your substitution. It's very important that you guys follow this. I will be marking you on your mathematical consistency. Limit has to be present the entire time until you're ready to start plugging values in for whatever your x is approaching. So please be consistent with that in your assignment so that you're prepared for the exam and it just comes as second nature. Here's one for us to try. You guys have a question? I heard some light pop on. Okay, try this example. Guys, I'm actually going to shut off your mics. If you need to talk to me, just turn them on manually. It'll work out nicer for the recording. Okay, the next thing I want to talk about is sometimes you will have to simplify to find a limit. Sometimes you'll have direct substitution, and we are getting 0 over 0, and you aren't able to factor, like you did in the last example. You may be able to You may be able to evaluate the limit by first simplifying the expression and then factoring later. Let's look at these examples. You have to do a little bit of work before you can even factor. So, here's our question. The limit as h approaches 0 of negative 2 plus h all cubed minus 2 bracket negative 2 plus h plus 4 all over h. Now, in my world, that's not the easiest trinomial to factor. And really, it's not actually a trinomial if you were to expand it. So you might have to simplify things first before you are able to factor. So what I'm going to look for is, to save some time, what I did was I expanded that term. Okay, you can either use Pascal's triangle to do that, or you can write it out 3 times, go the long way, follow the first 2, and then take that trinomial and multiply it onto another negative 2 plus h. Basically what I'm saying is you've got 3 of them. And I distribute the negative 2, and I'm now going to collect some like terms. Noticing the whole while, I'm including my limit. I get to a situation where I've got a trinomial now after I've got my terms. There is a potential for us to take out a common factor of h. Those h's are now cancelable, if that's a word, because we're getting the multiplication. And I'm left with a trinomial. 10 minus 6h plus h squared. There's no denominator now. I don't even need to factor it. I can just use direct substitution, and I get a value of 10. I'm not sure why the author included that step. It is something I would not have included, nor would I expect you to include. It doesn't do anything for us because the step above, he has canceled his h's, so really he should have maybe had this step there, but I think the author just got them out of order somewhat, but this step should go there. Once you have no numerator, people, like I said at the very start of the class, you're probably good to go to start using your direct substitution. Canceling your denominator is the best situation that you're going to encounter in order to evaluate your limit. All right. This example looks a little bit more difficult than the last, but it's a situation that I think we can try. You can't hear me? Okay, hold on, my batteries are dead. That's going to suck for this. Sorry about all the dead air that you're going to have on that recording now. So I'm going to go back to the example here now that you can hear me. And what I did was, I'm going to simplify what I can. Maybe that'll help us get rid of the situation that gave us 0 over 0. So what I did was I expanded this particular term and resulted in that particular section. I could have done that just on some scrap paper. Then I distributed the negative 2, and I received that particular portion, and the plus 4 is just there. Now I'm in a situation where I can just collect like terms. And that leads me to my next step. I have 10h minus 6h squared plus h cubed. I mentioned that you wouldn't have been able to hear me, that step there should not have been in this particular set of notes. I'm not sure why the author put that there. But let's ignore it for now. What I like about the author is they chose to take out a common factor of h. You can see where my cursor is kind of blinking there. and they canceled those h's, which will now take us to this step here, and our denominator is no more. When you get to a situation like that, direct substitution is probably your best bet. So I plug in 0 for wherever I saw h, and I got a value of 10. So the limit as h approaches 0 for that function would have been 10. Is that okay with you guys? I'm assuming quiet is yes. It's good. Let's look at this example here. It looks pretty scary, but it's not really scary. There is simplification to do. If I were to just cross this off, and if I gave you that question in Math 830, we all could have probably answered that, or simplified that. It's just a fraction with some x variables in it. Well, how do you add fractions? Well, you need common denominators, correct? So I'm going to let you guys try this one. See what happens. I'll just give you one little verbal reminder. Once you have one fraction over another fraction, my advice to you would be invert and multiply. You probably will see something cancel, and then once that occurs, you should be able to use direct substitution and come up with a limit. So I'll let you guys work on that one for a few minutes. Alright guys, I'm going to go through this one. So if you were finished, that's great. If not, maybe you want to watch. So I'm going to simplify the numerator. So I've got limit as x approaches 3. The denominator is going to be x minus 2, x plus 2. So the first one, I got x times x plus 2 minus 15 times x minus 2. That's going to be all over x minus 2, x plus 2. And that, of course, is all over x minus 3. Simplify my numerator. So I have x squared plus 2x minus 15x plus 30 all over again all over that. Continuing on, our collect like terms, I've got x squared minus 13x plus 30 So I can factor the numerator. I'm going to get x minus 10, x minus 3, all over x minus 2, x plus 2, all over x minus 3. Invert and multiply that, or if you are really on the ball, you know that you could probably cancel the bottom with the top. Invert and multiply. I can see a situation encountering those being reduced. I've got x minus 10, only on my numerator, all over. I'm at a situation now where I could probably start using direct substitution because the problem area has disappeared, and that problem area is when I plugged in the value of 3. So it's going to equal to 3 minus 10 all over 3 minus 2 all over 3 plus 2. So I get negative 7 on the top, 1 times 5, negative 7/5. Are there any questions for that one today? situation here? Okay, well, I've got a fraction in my numerator, so I'm going to circle that. This is what I have in green here. That's the same spot, right? And this fraction, x minus 3, is really x minus 3 over 1, correct? So I took this fraction and I inverted it to get that situation, 1 over x minus 3. And then now I can cancel those x minus 3s, because they appear both on the top and the bottom. And that will leave me with that situation, where now I can just start using my direct substitution. Does that help, Ashley? Okay. Now, in this case, there's another option. Typically, this option will only be used if you are involving radicals, because there's really, that's what rationalizing is all about. Okay. So direct substitution, once again, yields that 0 over 0. When you're dealing with radicals, you might want to consider rationalizing. Now, what you've done in the past in terms of rationalizing has been focusing mainly on the denominator. Okay. We haven't really let you have radicals in the denominator, so that's why we told you let's rationalize so we can get rid of them. Well, radicals in the denominator in calculus are not a big deal. Okay. We're allowed to have radicals in the denominator, and in fact, you'll see that you're even able to rationalize numerators. It's done the same way. Right? Just a quick, I'm going to add a slide here. If I had something like 5 all over root 7 plus 3, if we were to rationalize, remember, you've got two terms in the denominator, you're going to multiply top and bottom by the conjugate. So that is the same as what the denominator is, except that the sign in between the two terms is the opposite. So we would multiply top and bottom by root 7 minus 3. So at the top I get 5 times root 7, I get 5 root 7 minus 15. And on the bottom, you can kind of cheat fall because they're really different as squares. What I mean by cheat fall is go that times that, and make that times that. You don't have to do the insets because they'll end up canceling. So root 7 times root 7 is 7. Positive 3 times negative 3 is minus 9. So I would have 5 root 7 minus 15 all over negative 2. And that was what you've done in A30. So just a quick review going back there for us. Let's look at what we will encounter in this situation. So, here's our example. As x approaches 100, of root x minus 10 all over x minus 100. Direct substitution, if you just quickly take a peek at it, you're going to end up getting 0 over 0. Okay. Here, our radicals are in our numerator. We can still rationalize. We just rationalize the numerator. Done the same way using the conjugate. So there's a bunch of material that I just mentioned out loud. You can see how we multiply top and bottom by the conjugate, and here's the conjugate here. And you're able to multiply by the conjugate because really that's multiplying by 1. You haven't changed the question at all. So, I'm going to FOIL the top. But I'll give you a hint. Okay? You won't need to, and I would prefer you to not FOIL out this bottom part. And it's not always going to be on the bottom. Right? It might be on the top. You want to FOIL out the ones that's the difference of squares, because that's going to get rid of it. It happened to be in my numerator in this question. In the question I dealt with you guys just a second ago, it was in my denominator. So it is very easy for people to just jump in and start foiling this out, but trust me, you're just going to end up wasting your time because We can get rid of the problem area with radicals, and that's going to be wherever you had the radical in the first place. You won't need to do the other part. So it's going to be one or the other. You can see I didn't even FOIL that bottom part. Once I got to this situation here, okay, I'm able to now, you can see, cancel. And you wouldn't have been able to cancel if you were to FOIL this out. You never understand what I'm doing now. Okay. If you were to multiply that out, you would have to have gone back and refactored it in order for you to cancel. And that's the whole goal of rationalizing either the numerator or denominator. If you want to be able to cancel something, and there's where I'm canceling. As the author is showing, he's now left with 1 over root x plus 10. Direct substitution is now alright, because I can plug in 100. Root 100 is 10, so I get 1 over 10 plus 10, or 1 over 20. I'm hoping there's an example for it. This one looks scary, but it's really not. Okay? It's not scary at all. And you'll see what happens when you guys try it. So give this one a go. I will throw that up there in case you want to look back.